Introduction, George Green's 1854 essay, an essay on the application of mathematical analysis to the theories of electricity and magnetism, represents a culminating testament to his profound contributions to mathematical physics. This work synthesizes and extends his prior explorations, crystallizing his thinking on the interplay between mathematics and physical phenomena, particularly in the realms of electricity and magnetism. This essay undertakes a detailed, section-by-section assessment of Green's treatise, aiming to delineate his specific claims, scrutinize his arguments, and weigh his enduring significance. The evaluation prioritizes the internal consistency and logical coherence of Green's exposition, situating his contributions within the progression of scientific thought. Through this rigorous analysis, the essay seeks to determine Green's influence on the evolution of these scientific fields. Section 1, Foundational Principles and Mathematical Preliminaries. The initial segment of Green's essay establishes the mathematical groundwork essential for his subsequent analyses. It begins, directly, with discussions of potential functions, specifically the concept of what is today known as Green's function. He constructs his arguments from first principles, building from the mathematical framework to address the physical problems. Green's exploration of potential functions emerges as a central element. These functions, in Green's treatment, serve as tools for resolving problems in electrostatics and magnetostatics. He presents methods for calculating the potential at a point due to a distribution of electric charges or magnetic poles. Crucially, Green establishes that the potential at a given location is a result of the influence of all other sources in the given space. The elegance of Green's approach resides in his development of an integral representation for the potential, which facilitates the solution of boundary value problems. This allows relating the potential to the distribution of charges or pole the geometry of the space in which they are This section elucidates the principle of superposition, which Green employs within his formulations of the potential. He argues that the overall potential at a point is the sum of individual potentials from all sources present. Green's argument relies on a certain mathematical linearity, which would later become a basic premise in electrodynamics. Green's meticulous mathematical treatment of potential functions serves as a firm foundation for the ensuing discussion of electricity and magnetism. Section 2, Potential and the Inverse Square Law. This portion of Green's work dedicates itself to the relationship between electrical potential and the inverse square law characteristic of electrostatic forces. It provides a lucid examination of the relationship between electrical charge and potential, offering an analytical approach for understanding how these interact. Green explains the inverse square law in depth, demonstrating its mathematical basis under the framework of potential theory. He demonstrates how the potential, caused by a point charge, diminishes with the square of the distance from the charge. Through this, Green solidifies a mathematical framework for understanding the force of electrical repulsion. The specific derivations presented in Green's work are critical and show his capacity for insightful application of mathematical analysis to the complex phenomena of electricity. Furthermore, Green's argument includes the concept of equipotential surfaces. He discusses how these surfaces, where the potential remains constant, are perpendicular to the lines of force. He connects potential with lines of force. He explains the concept of potential in a mathematically rigorous fashion, adding to the foundational development of electrical physics. In essence, this portion of the essay lays the groundwork for the application of Green's mathematical methods. It provides a clear picture of the connection between potential and the distribution of electrical charges in a static field. It underscores the profound impact of mathematics in the elucidation of physical principles. Section 3, Exploring the properties of electrical and magnetic fields. Green next delves into the mathematical properties of electrical and magnetic fields. He introduces the concept of a force function, laying the foundation for his method. His work demonstrates that electrical forces are potential, meaning that there exists a scalar function, the potential, whose gradient describes the forces involved. Green's analysis then extends into the properties of the electrical field, wherein he examines the concept of an electrical field as a function of position. The intensity of the electrical field is understood as the gradient of the potential, which means it points in the direction of greatest potential decrease. This is a central idea in Green's formulations. Green discusses how electrical fields can be derived from the distribution of charges. Green subsequently examines the properties of the magnetic field, similarly applying the concept of potential and force functions. Green demonstrates the analogy and conceptual parallel between electrical and magnetic fields. He illustrates how the forces in magnetic fields can be seen as deriving from the distribution of magnetic poles. This section lays the conceptual groundwork for later developments. It develops the framework that allows Green to derive several significant results. Section 4 Surface integrals and Gauss theorem. Within the mathematical framework, Green introduces surface integrals and the subsequent application, often referred to as Gauss theorem, to electrostatics. This significant section builds upon his earlier, foundational work, providing a further means of linking mathematical and physical concepts. Green articulates the connection between the flux of a vector field across a closed surface and the sources of that field contained within the enclosed volume. This fundamental theorem emerges as a link between the local behavior of a field, determined by its sources, and its global behavior, measured by an integral over a closed surface. He expresses elegantly his mathematical derivations. Green applies this theorem to the electrical field, demonstrating that the flux of the electrical field across a closed surface is proportional to the total electrical charge enclosed within the surface. This is the essential insight from Green's theoretical work. The development of this relationship, known as Gauss' law, is a cornerstone of electrostatics. Its importance is evident throughout the subsequent development of electrical theory. In a similar vein, Green analyzes the magnetic field, applying the theorem to derive the analogous relationship for magnetostatics. He provides the link between the flux of the magnetic field and the magnetic poles enclosed within a closed volume. Green further refines the relationship by recognizing the absence of magnetic monopoles, meaning the flux of the magnetic field always returns to zero. Section 5 Green's theorem and its application. Here, Green leverages the theorem named after him to solve boundary value problems for the electrical potential. Green's theorem, a cornerstone of the work, offers a powerful tool for determining the potential function. The application of this theorem is the central contribution of this particular segment. Green applies his theorem to specific examples, especially in the context of charged conductors. He demonstrates the unique solution of the potential within a given volume when either the potential or its normal derivative is specified on the boundary of that volume. This constitutes a profound insight, establishing the uniqueness of solutions in electrostatics, which greatly simplified the task of solving boundary problems. Green continues, exploring the use of Green's functions when dealing with various boundary conditions by showcasing how these mathematical tools allow for the transformation of differential equations into integral equations. This provides a technique for obtaining solutions to complex electrostatics problems. Green's theorem, together with the development of Green's functions, provides a potent mathematical framework for tackling the problems in electrostatics. Section 6 Problems in magnetostatics. Green applies his mathematical methods to magnetostatics. He outlines how he would develop a mathematical treatment of magnetic phenomena analogous to the electrostatic framework he had described. Green shows how the concepts of potential and force functions, as well as the mathematical machinery from the previous sections, can be effectively applied. Green elaborates on the concept of magnetic potential and its association with the distribution of magnetic poles. He formulates the integral expressions for the magnetic potential, which are analogous to the integral expressions for the electrical potential, thereby demonstrating the similarities between the two fields. This section provides the conceptual link between electrical and magnetic phenomena. Green's essay underscores the importance of understanding the mathematical nature of the magnetic field. He shows how the magnetic field can be derived from the magnetic potential, and how his approach can be used to determine magnetic fields and their interactions. Section 7. The connection to previous theories. Green's essay offers context to earlier theories, grounding his work within the existing intellectual climate. He references the work of previous scientists such as Poisson and others, which were essential in the foundational development of electromagnetism. He describes their insights and how his own work builds on prior discoveries. Green assesses the contributions of others, showing both the areas of agreement and those where his advancements go beyond what was already known. Green's essay provides a lucid illustration of a scientist building upon the foundations laid by his predecessors. The contribution of Green to electrical and magnetic theories reveals his role in the scientific development of the time. Section 8. Implications of Green's work. This section contemplates the implications of Green's work, particularly in electrical and magnetic fields, that could be applied to the analysis of electrical and magnetic phenomena. He demonstrates the applicability of his work not only on the theoretical understanding of fields, so on practical problem solving within those domains. Green's approach provides valuable tools for calculating electrical and magnetic fields in various situations. These tools, including potential functions and Green's functions, can be applied to diverse problems involving various geometries and distributions of charges. The implications of Green's work extend to the areas of engineering and technology. Section 9. Evaluating the methodology. This section focuses on Green's method of mathematical analysis. The essay underscores that Green's methodology is rooted in a rigorous and systematic approach, deriving solutions from first principles and using precise mathematical tools in his explorations. Green's approach prioritizes a mathematical framework, using complex mathematical analysis, like the development of integral equations. His method is marked by clarity and precision. The methodology is useful because it provides a degree of accuracy and clarity that is crucial in scientific problem solving. The essay assesses the overall quality of Green's work by investigating its reliance on sound logical reasoning and a mathematical elegance. The conclusions of Green's work are based on a solid understanding of mathematical physics, which is essential for advancing the knowledge of electrical and magnetic phenomena. Section 10. The legacy of Green's work. The ultimate segment of this essay discusses the lasting impact Green's work has had on the development of electromagnetism and, in a wider context, on the history of science. Here, the essay describes both the direct and indirect influences of Green's work. Green's insights into the methods of problem solving in the fields of electricity and magnetism have left a profound mark on scientific thinking. The methods, including Green's theorem and the use of potential functions, are still fundamental to the resolution of scientific problems. The essay explains how Green's ideas have influenced the development of physics. Further, Green's work is pivotal for shaping the direction of scientific research. The contribution of Green to the conceptualization of electricity and magnetism has helped to guide the investigation of these fields. Conclusion. George Green's 1854, an essay on the application of mathematical analysis to the theories of electricity and magnetism, stands as a monument to the power of mathematical analysis in illuminating physical reality. The analysis here confirms that the work's strength lies in its systematic development of mathematical frameworks for understanding electrical and magnetic phenomena. Green's introduction of concepts such as potential functions, the inverse square law, and Green's theorem provides essential tools for solving boundary value problems and understanding the behavior of electric and magnetic fields. His rigorous application of mathematical principles solidifies the arguments presented, demonstrating an insightful approach. Green's work offers a model of scientific rigor. It demonstrates the power of mathematical modeling Opening the way forward for future scientific exploration, the essay serves as more than a collection of equations and concepts. It functions as a window into the world of scientific inquiry, showing how a scientist builds a framework of knowledge. The influence of Green's work extends beyond the bounds of physics, enriching the broader intellectual landscape. The significance of Green's insights into his chosen fields speaks to his lasting influence on scientific thought.